Hello, welcome to Chaos and Controls, a show where we talk about modern devices, technologies, and techniques for automating your home, business, or life. I'm your host, the Automation Doctor. Today, I thought we could go ahead and continue last episode's video just a little bit, and talking a little bit more about the fundamentals of logic, and specifically how we can actually represent the same information in multiple ways. Now, last time, I believe we talked about a garage door, but let's go ahead and assume that I have just a regular door that I want to grant access to somebody, and I have some method of electronically allowing somebody to come through the door. And so some of the things that I might have, I could have a normal key that just opens the door, and then I might also have a code pad that you can type in a code, but that in and of itself, I don't want to be able to just give away the code to anybody, so I'm also going to integrate maybe a fingerprint scanner. And if I want to represent opening the door, over here would be my output, which I can also say is open the door. We can draw what we call a truth table. And I have 3 inputs, 1 output, 0, 1, 0, 1, 0, 1, 0, 1. Every second one, 0, 0, 1, 1, 0, 0, 1, 1. Every fourth one, 0, 0, 0, 0, 1, 1, 1, 1. Let me go ahead and draw in some lines. Have a true engineer and or doctor's handwriting, so please forgive that. And you'll notice that the reason that I drew in this specific pattern, 0, 0, 0 in binary is 0, 1, 2, 3, 4, 5, 6, 7. I have 3 inputs, and so I have 2 to the 3 is equal to 8 combinations, but we have to do something to make it easier for the computer, so we start counting at 0. 0 to 7 is 8 possible combinations. So now let's go ahead and start filling this in just a little bit. And obviously, if somebody comes up, they don't have a key, a code, or a fingerprint, I decidedly do not want my door to open. If all they have is a fingerprint, maybe I want them in, but again, fingerprints are, depending on the technology using, not necessarily the most difficult thing to spoof, so no, I'm not going to let you in. And same thing with a code. If somebody just overhears the code, I don't want them to be able to walk through my front door. But if you have a code and a fingerprint on file, sure, I'll let you in. Or if you have the key, I gave a physical key to somebody, sure, we're going to go ahead and let the door open in that regard. And so this is what we call a truth table, because based on all of my inputs, I can see my outputs, and we can derive how this system should behave. But I want to go ahead and express this in a way that I can program it. And as much as we could put together this truth table and just store it somewhere as a reference table, that's not the most efficient thing. And so one of the methods that we can use to derive an equation for this is called a Carnot map. Now, you probably won't come across Carnot maps very much in the wild. They are still taught, and they're really useful for any time that you have, we'll say, 3 to 5-ish digital inputs. Up top, I'm going to put whether or not I have the key, no and yes, and over here we're going to do a combination of our code and fingerprint. And over here, we're going to fill it in with what is called gray code. And gray code just means that I can only change 1 bit at a time. So even though the next counting number would be 1, 0, so we can go 0, 1, 2, in gray code, we would do 1, 1, so that the only bit we flipped was this one. And now, you'll notice 0, 1, 2, 3, 4, 5, 6, 7, I can just go to my truth table and fill these in. 0, 0, 0, 1, 1, 1, 1, 1. Same information. Let me move that up a little bit. Same information represented a slightly different way. The advantage of a Karnaugh map is that I can start grouping things together. And I can group anything that is in a binary pair. So 4 is a binary number, 2 is a binary number. And what is common over here in all of these is that I have a key. So I can say, open the door if I have a key, or what's common here, the key is 0 and 1, so that's different, but what's common between them is I have a code and a fingerprint. So I have a code and a fingerprint. That is starting to look more like something we can put into a computer. And so I took the truth table, put it through a Karnaugh map, and made my formula over here. Remember, plus is the logical equivalent for an OR, and multiply is the logical equivalent for an AND. The next thing that we're going to do, or if we wanted to represent it also in this format by using gates, I could say I have my inputs key, code, and fingerprint, and we said that in order to open, it takes a key or a code and a fingerprint. This is an OR gate, this is an AND gate. All of these are the same information represented a different way. Now, we'll do more examples in future videos, I have no doubt, but just wanted to give an example of how we might take an actual problem that we are trying to resolve, how we can derive for every solution and every situation we account for in a truth table, and then how we can then translate that into something we can either put into code or that we can physically program with logic gates, which isn't something you see so much anymore, but think like fully programmable gate arrays. This would become useful for you. In any case, that's about all I have for you today. You all have a good one, and I will catch you next time.